Okay, I hope everyone can see the slides. Is it true? And do you hear me, by the way?
Yeah.
Okay, thanks. Yes, so just in case if you have any questions, please, it's better probably to write them in the chat, and I hope I will notice and then I will reply. Also, okay, let me, okay, so unfortunately, last time the lecture was only partially recorded, so I will repeat some part of the material, and that's why I prepared the slides. It's just for the quicker process, but then later we'll probably switch back to the standard classical board lectures. Okay, so let me recall that this classification theorem of hyperbolic isometries. If F is an isometry, we can denote by F bar its extension to the compactified hyperbolic space, which means which is basically a closed ball, right? It is the interior of the hyperbolic space plus the sphere, which is ideal hyperbolic boundary. We'll basically conflate F and F bar, meaning that automatically, if we have an isometry, it acts on the boundary. Okay, then F is said to be elliptic if the fixed point set of the F in the hyperbolic space is not empty. So classical examples are reflections and rotations around points in the plane, rotations around axes, geodesic axis in the three-dimensional hyperbolic space. The second type is parabolic, and F is said to be parabolic if the fixed point set of F itself inside the hyperbolic space is empty, but there exists one fixed point on the boundary. Classical examples are parabolic rotations around the infinite point in the upper half plane model, where the action is z to z plus a, some real number. So just really translation along a horizontal or a circle, which what we'll see later. And it is said to be, F is said to be hyperbolic if again the fixed point set of F is empty in the hyperbolic space, but we have precisely two fixed points on the boundary. Again, classical examples are hyperbolic translations. For example, just Euclidean similarities in the upper half plane model, z maps to lambda z, where lambda is some positive real number. And this is a translation along a vertical half line from 0 to infinity, right? So it's a vertical geodesic defined by equation x is equal to 0. And now in my fixed points here are, where is it? Yeah, so p is 0 and q is infinity. Okay, great. Then we also discussed horospheres in the last lecture, and we will use this material today. So I will just quickly remind what is it. So if P is an ideal point, so it's a point on the boundary or a point at infinity, then a horosphere O of P centered at P is a hypersurface which is orthogonal to all geodesics starting at P. One can view this as a like sheaf of oh, actually it's not a sheaf, it's actually a sheaf of, so there is a sheaf of geodesics passing through P, right? But it's the bundle of horospheres. So I will, yeah, sorry about that. I will change this in the slides. So we have, in fact, the bundle of pairwise disjoint horospheres. And in the previous lecture, we discussed that in the upper half space model, we can take P being the just infinity, and then any horosphere is just a horizontal Euclidean hyperplane. And this can be identified with the d-1 dimensional Euclidean space. And in the vector model HD, our horospheres are the like the sets defined as follows. They consist of vectors x such that the scalar Lorentzian scalar product with P is constant. And again, by just we can vary this constant and we get again a bundle of four spheres. Yeah. Okay. A very important remark is that parabolic isometries fixing P leave every sphere at P invariant. Moreover, so we do not move one sphere to another. This is in fact a part of the proof that parabolic isometries are Euclidean isometries, right? As in this example, z to z plus a, it just acts as an isometry in this horizontal line. Generally, in higher dimensions, my parabolic isometries leaving the infinite, right, the infinity invariant in the upper half plane mode, in the upper half space model, they act as Euclidean isometries in horizontal hyperplanes. Okay. As a consequence of this fact, the stabilizer of the full isometry group of HD and the stabilizer of the, I'm taking the stabilizer of an infinite point, of the point at infinity, P, it thus coincides with the full isometry group of the Euclidean d-1 dimensional space. Okay. Then another notion I'm going to use is the barycenter. And actually, so the classical, like simplest case of barycenter is just the midpoint of the segment. And let us consider this simplest case first. So the question is, how can one find the midpoint of the hyperbolic geodesic segment in HD? I'm taking x and y in the hyperboloid in the vector model. And then we note that the sum of vectors x plus y satisfies the following. First of all, the square v times v with, so the scalar product of v with itself is definitely negative. Well, you can just write down x plus y times x plus y, then expand, and then you will see that you will get x, y, right? Both are -1. And also you obtain 2 multiplied by x times y. And since we know that x times y, so the product of x and y is negative, the entire scalar product is negative. Moreover, which is also very important, that, so, well, the fact that v times v is negative implies that it can be rescaled in such a way, in such a way that the zero coordinate is positive, and the scalar product is equal to -1. Moreover, it can be rescaled by some positive number in such a way, since the zero coordinate of v is initially positive, right? It's so our x and y both have x0 and y0 are positive. So when we take the sum, we obtain a positive zero coordinate. This means that our vector kind of looks, so it heads towards the upper half sheet of the hyperboloid. The only question is how to rescale it. And what is very important for us, v satisfies that the following: the scalar product of v with x equals the scalar product of v and y. And here is the computation, right? I just again expand and notice that x times x is equal to y times y is equal to -1. And so it remains to see that the vector v normalized by this Lorentzian norm, it belongs already to the hyperboloid model of the hyperbolic space. Definitely, I'm using here the fact that the hyperbolic cosine of distance between 2 points, right, is expressed via the Lorentzian scalar product, right? Okay. Now the definition so this the barycenter, the general definition of the barycenter of a finite collection of points. So generally, if I have k points p1 and so on pk in the hyperbolic space, I can define the point being just p1 plus and so on pk over the Lorentzian scalar product. It will also be a point from the hyperbolic space, and it is our barycenter. In fact, it's indeed so to be more precise and to be like more similar to what is to the way how it is defined in the Euclidean space, I actually should have written here 1 over k in front of this sum and 1 over k in front of this sum in the denominator, but this is going to be killed, right? So again, just a footnote that this denotes the Lorentzian norm. The Lorentzian norm is defined as the square root of the absolute value of v times v. So it's here we will have minus v times v if v is if it has negative Lorentzian square. Okay. Well, so so for example, this will give us it's just very similar to what is done in Euclidean geometry. Okay. Then I'm going to discuss cyclic groups of isometries. So let F be an isometry of the hyperbolic space. The question is, what can we say about the powers of F? F to the power of k is just the composition of F with itself k times. Then there is the following proposition: let k be any integer. In fact, k can be equal to 1, but when k is equal to 1, it's not interesting. So let us start with something already more interesting. So F, then if F is elliptic, then any power of F is either elliptic or trivial. If F is parabolic, then Fk is parabolic and non-trivial. And if F is hyperbolic, then F to the power of k is hyperbolic and also non-trivial. So in particular, if F to some power of S is an identity isometry, is the identical isometry, right? Then F is elliptic. So this means that only elliptic isometries can be of finite order, right? But this remark says that, however, not all elliptic elements possess this property, which means, so like a nice example is that take a rotation in the hyperbolic plane at angle pi alpha, where alpha is irrational. You can consider this isometry in the ball model B2 and just take this rotation around the origin. This is going to be just a standard Euclidean rotation, and you will see that it's never, so it is not a, it is an element of infinite order, right? So again, this is actually important. Elliptic elements, only elliptic elements may have finite order, but nevertheless, there exist elliptic isometries of infinite order. All other isometries, parabolics and hyperbolics, are infinite order, and their powers preserve the type of this isometry. Okay. Now the proof of this proposition. We start assuming that F to the power of k is elliptic, is an elliptic isometry for some k. So suppose that f is some power is elliptic. Okay, then there exists an element x, obviously, such that f to the power of k of x is x, right? F of k, fk is elliptic, which means that we have some fixed point. Great. Then we consider a cyclic group generated by this isometry f. That's why this section called cyclic groups of isometries. And this group gamma gives us the gamma orbit gamma x, which consists of how many? K elements, right? And an isometry, our isometry f, it simply permutes the elements of this orbit. So the entire orbit definitely lives invariant under the action of gamma, obviously, and under the action of f in particular. Okay, thus f lives invariant the barycenter A of the finite set gamma x. And this is crucial. You see, just recall how the barycenter was defined, right? It was the sum, right? It was the sum of finitely many points, and the whole collection is invariant. Obviously, the sum also remains invariant under the action of f, right? But this is one point, and this point is thus fixed by our isometry f. Yeah. So far it's clear. Okay, then which means this implies that f is elliptic, right? Okay, then so we basically showed that we already proved that if some power is identity, then so if some power is trivial, then it can be only hyperbolic. Sorry, it can be only elliptic element, right? And then also this consideration, this implies that every power, right? So if f was initially elliptic, then obviously f to some power of, so fk of x for any k also preserves x, right? So this was the hardest part. Now it remains to know that if P is the ideal bound, is the point from the ideal boundary, and F preserved P, then any power of K also preserves P, right? So if F is parabolic and that such a P is unique, then F lives invariant the Horosphere is centered at P, and so does any power of K, right? Therefore, so we know that Fk is definitely not identity, right? It lives invariant the Horospheres, but if it lives invariant the Horospheres, it is also parabolic since it acts just a Euclidean isometry in the, like, imagine it's a horizontal hyperplane in the upper half space model. Then f to the power of k is parabolic as well, right? Finally, if f fixes 2 points on the boundary, then so does every fk as well, right? So it fixes precisely 2 points. Then it can be, since we already proved that it cannot be, right? It cannot be an isometry, sorry, in the identity, right? It is not a trivial isometry. Then it should be of the hyperbolic type, right? So one should be careful with this classification, right? If you found 2 fixed points, it is not enough. You need to, so elliptic isometries, they have fixed points from the boundary as well, right? So for example, reflections. So what you need to check basically need to check that you have precisely P and Q. So we first show that f k, right, f to the power of k, we show that it has two fixed points, but then we say, okay, f to the power of k is not elliptic, right? Since if fk was elliptic, then f is elliptic. Okay, then we know that since fk has at least two fixed points on the boundary, it is not trivial, it is not elliptic. This implies that fk should be hyperbolic. Okay, so this cyclic group theorem is proved. Now let me recall some facts about homogeneous spaces. I already gave some information somewhere in the beginning, but let me repeat. We will again use it a little bit later. So let G be a diffeomorphism group acting transitively on a smooth manifold X, and P just be some point from this manifold X, right? Then the stabilizer H of P is a closed, actually, subgroup of G, and the quotient G mod H is naturally identified with X. The identification goes as follows. You identify the classes, right, the cosets of G mod H with elements of X, and you use the fact that you have a transitive action. This is actually a diffeomorphism. Well, in fact, this can be stated in a broader setting of just topological group acting transitively on a topological manifold, then you will have a homeomorphism. But if everything is in the smooth setting, then it is a diffeomorphism. So in this case, right, we have this natural identification of the manifold X with this quotient G mod H. So I remind that in the case when we considered the quotient by complex subgroups, this manifold X, which is G mod K, it can be equipped with a G invariant Riemannian metric. So in fact, it can be made a Riemannian manifold such that G is a, okay, it's not necessarily the full isometry group, but it's, I would say it contains the identity component, the component of the identity of the full isometry group, okay? So G is some isometry subgroup of the manifold X in this case. So classical examples are Euclidean spaces. So in all these cases, the stabilizer of the point in the space is just the orthogonal group of order D, and I just wrote down different spaces with their different G, right? And for the sphere, it is OD plus 1, and for the hyperbolic space, it is the projective orthogonal group of the Lorentzian form of signature D1. Okay, then another example of how one can use this homogeneous spaces technique is the following. We remember that G, right, the full isometry group of the hyperbolic space, it is generated by reflections in hyperplanes in the hyperbolic space. Our hyperplanes, okay, those reflections, they act on the boundary as inversions with respect to hyperspheres, right? So like geometrically, it looks like we have a hyperplane, it intersects the boundary in some hypersphere, sphere of codimension 1, right? And the action of the reflection on the boundary gives precisely the inversion with respect to this subsphere or hypersphere of codimension 1. So then this isometry group can be identified with the extended conformal group. Extended means that it contains both conformal and anti-conformal maps. So our inversions with respect to hyperspheres are they are actually anti-conformal maps, right? So remember that you need so for being conformal in our classical, in our definition, you need to have so the differential should be composition of the right of some similarity and orientation preserving isometry. And inversions give you, in the differential, they give you orientations reversing isometries. So that's the idea. Okay, then we also remember that the action on the boundary is transitive. And we just discussed that for every ideal point, the stabilizer GP is the isometry group of the Euclidean d-1 dimensional space, which is the horosphere at P, right? And thus, we have that the sphere as d-1, or the boundary, is identified with the following homogeneous space. It's a very nice fact. It just follows from the above, right? It just follows from this. We need to take the quotient of G by the stabilizer, which is the isometry group of the Euclidean. So, but as d-1, so it has its natural metric, but this metric will not be G invariant, where G is the hyperbolic isometry group. Okay, so you see this guy over here, it is not compact. Yeah, just compare this to this. Okay. Yeah, okay, let's move next. Now I'm finally ready to define discrete groups. Again, I'm repeating this, but yeah, that's okay. So here X in general, it is just some good geodesic metric space where good includes, so it covers all nice homogeneous symmetric spaces G mod K, and in fact, something else can be included, but for the purposes of our course, it's totally enough to think of just homogeneous spaces. Here I mean symmetric, since in fact our G mod K, they will always allow to get the involutive automorphism of the Lie group G, which gives us the involution at the point, at any point of the space X, right, G mod K, and these are the so-called symmetries, and then the spaces are called symmetric or Riemannian symmetric spaces. We are not going to just we're not going to go into some details of that, but this is this is a very broad class of spaces. But actually, yeah, something more complicated can be considered. So by definition, a subgroup gamma is said to be a discrete isometry group or a discrete group of isometries, or sometimes it is said the discrete group of motions of X if all gamma orbits, gamma X, are discrete in the space X and all stabilizers are finite. So what is interesting here? In the case of symmetric spaces, when the isom of X is a Lie group, then this definition is equivalent to gamma being just a discrete subset of G. So remember, G is a Lie group, which means that G itself has a structure of just a smooth manifold, right? So we can just define a standard. We can just get some standard things like neighborhoods of points, right? Neighborhoods of elements. So if you have a manifold and if your subgroup sits there as a discrete subset, meaning that some neighborhood of every point doesn't have any other elements in the set, then it's discrete, right? So if just a discrete subset of G or a discrete subgroup, then it's equivalent to being discrete in this initial sense. And in this case, actually, the second condition in our definition can be omitted. It holds automatically since stabilizers, right? These guys, stabilizers, this is the subgroup of gamma, right? It consists of all elements that fix some point x, right? It is definitely the subgroup of the stabilizer Gx, right? If you take the full isometry group and you consider the stabilizer of x in the full isometry group Gx, then gamma is the gamma sub x is the subgroup of G sub x. But then let's get back here. G sub x is just a compact Lie group. And you know that you have a discrete, right? So now use this. Gamma is a discrete subset of G. Then gamma sub x, the stabilizer, is the discrete subset of G sub x. So this is a discrete subset of a compact group. But this implies that it should be finite, right? You cannot have infinite discrete subsets of the compact. Otherwise, you would have some accumulation points, which contradicts the discreteness of gamma, right?
Well, this is not completely true. This is the important thing is that this is a compact subgroup, not subset.
Yes, it's a compact subgroup. Yeah.
I mean, yeah, discrete subgroup of a compact space, of a compact subgroup, not just subspace. Yeah, you can have a compact space with discrete subset, which is not
Yes,
compact.
but yeah, in this case, it is basically it's just a compact. It's a nice compact subset. Since it's a compact Lie group, it's a nice compact subset in Rn, and then it's already enough to conclude that you should have finite stabilizers. Yeah, thanks for the comment. Okay, then let's consider some examples. So examples are this. The first example is quite simple, is just the group gamma Z, which acts on the real line R by translations. X maps to x plus a, where a is an integer. And obviously orbits are discrete, right? They form basically something isomorphic to Z itself in the real line. So in fact, if you take an element X, then its orbit is discrete, since you can take, say, the interval of length, or you can take 1/2 neighborhoods, right? A neighborhood which just gives you, right, an interval of length 1 with midpoint being X, it certainly gives you the neighborhood which doesn't intersect with other points of the orbit. Then you can also notice that stabilizers are trivial in this example, right? Since these are translations. Okay, the next example is also simple, it's just an extension of the previous one. You take the group Z squared acting on the real plane, which is the Euclidean plane, by translations again. So these translations just are translations with respect to vectors having integer coordinates. And again, orbits are discrete grids in the plane. Yeah, you just can see them as very nice grids in the plane or a lattice. And stabilizers are also trivial in this example. Okay, the next instance is already a bit more complicated. It will have non-trivial stabilizers. And it's obtained as follows. Take the square tiling of the Euclidean plane. So you just basically take the integer grid, right? And you just draw all vertical and horizontal lines having, well, passing through integer points on axis X and Y. It gives you the tessellation of the plane by identical copies of the squares. And you can take a group gamma generated by reflections in the size of those squares. In fact, it's enough to take just one square. Oh, no. Yeah, it's enough to take one square, say this one, right? And just generate the group gamma by 4 reflections. Okay, then let's think of orbits. And this is drawn here on the picture. I just took one point, then I need to reflect it to the right. It gives me this point. Then I reflect it to the top. I'll get this, then this, and so on, right? So you see, it also looks like a grid, but already, so it's definitely a discrete subset, but it's already, it's not the same as the orbit, right? It's not the same as the orbit for the group Z squared. But actually, what is interesting, it contains the subgroup Z squared. You see, if I remove this element, then my translation, so I can take, so I need basically to remove this 2 and this one. Then what I see is that this point is obtained from this one as just a translation, right? It's composition of 2 reflections. It is a translation always. So the composition of these 2 reflections, right, with respect to 2 adjacent, well, 2 parallel lines gives me the vertical translation. And the group generated by these 2 translations is definitely a subgroup of my reflection group. And so we can see that Z squared appears as a subgroup of the reflection group. Both are discrete. But in this case, we have already non-trivial stabilizers, since reflection itself, light reflections itself, they fix all these lines pointwise, right? So all these lines, vertical and horizontal lines, are fixed. And it is that, so for example, the stabilizer of this point in our group is just Z, the quotient of Z mod 2Z, right? Since it's fixed by precisely one element of order 2 of the reflection. But if I take the stabilizer of this point, which is at the intersection of the two horizontal and the vertical lines, then the stabilizer is already a bit bigger, right? It is generated by 2 intersecting reflections. So something like that we have in this picture. But these stabilizers are finite groups, so everything is nice. Yeah? And in fact, the fact that it's already, so we already found that the orbits are discrete. Again, we kind of use some intuition here, but yeah, this implies that stabilizers should be finite, as we previously discussed. Okay, then hyperbolic examples. So those were Euclidean examples. Now a couple of hyperbolic examples. I can also consider actually a group Z acting in the hyperbolic space. Well, first of all, hyperbolic line is just a real line, so it's not that interesting. It will also act discretely on the hyperbolic one-dimensional geodesic. It is similar to the action on the real line, right? But now I'm taking the group gamma acting by translations in the upper half plane model, z maps to 2 to the power of k z, where k is some integer. And you see, I just took the point I in the upper half plane model, and this is its orbit, right? It is discrete, definitely. It converged, it has two accumulation points, 0 and infinity. But these are not the points of the hyperbolic space, these are points of the boundary, right? So the orbits are discrete, and again, the stabilizers are trivial here. The stabilizers of the interior points of the hyperbolic space are trivial, but we have the points at infinity that are stabilized by this isometry. Okay, the second example is an example generated by two hyperbolic translations. And the picture is here. Also take the tiling of the hyperbolic plane. And this tiling can be obtained as follows. Take a regular, so very symmetric regular orgon having having four ideal vertices on the boundary. Imagine this just the vertices of the Euclidean square, right? Inscribed in this unit circle, right? But then you join these vertices by the hyperbolic geodesics, by the by the arcs orthogonal to the boundary. Then you can take two translations. They are shown here in red. So we have since these are disjoint, right? The opposite sides of the square are disjoint. We have a unique orthogonal geodesic, which is orthogeodesic, which is orthogonal to both of the opposite sides. And then one can take a translation G1 that maps this blue line to this blue line, and the translation G2 that sends the like horizontal to the horizontal line, whatever it means, since these are arcs. And then the group generated by these two translations gives you the tessellation. So it acts on the plane, and you can take this tile P, this foregone, and you will tessellate you will just tessellate the entire disk by those squares. Okay. Then you see that this group is actually, we will see it a bit later, that this group is actually isomorphic to the free product of two copies of Z. We have no relations between these two generators, G1 and G2. And the orbit is shown here, and in each tile you will have some neighborhood sitting inside of this tile. So the orbit is discrete, and again, the stabilizers are trivial in this example. All right, I think that it's time to make a 10-minute break, and then we will continue. So we will resume at 5:10. Okay? Okay, I think we can continue. So we considered examples of discrete groups of isometries. Okay, there is one interesting phenomenon in the hyperbolic space, that there exist non-discrete groups with two generators, even in the case when the generators separately give you discrete infinite cyclic groups, right? So you can notice that in the hyperbolic, notice that in the Euclidean space, say, if you take two translations in different directions in the plane, you will always actually get a discrete group, Z squared. The only point is that on this picture, on the oh, I didn't have this, I don't have this picture, but so assume that you have this square tiling, but instead of square tiling, you will get parallelogram tiling, and then your group Z squared will be generated by translations with respect to another choice of basic vectors. That's basically the difference. But it's always it'll always be discrete. And in the hyperbolic space, it's not the case. It may happen that a group gamma is not discrete if both G1 and G2 give you discrete cyclic, infinite cyclic groups. And this example, I just provide some concrete example. And this example is obtained as follows. You take two, so one can pick two isometries, G1 and G2. The first one acts, so it is in the upper half plane model. The first one acts as the homotheity with coefficient 2, Z maps to Z, right? It is a hyperbolic isometry. And the second isometry is the parabolic translation Z to Z plus 1. And I would like to highlight one fact here, which is the crucial, like, actually, this is a crucial obstacle for being discreteness. And the point is that this isometry, it fixes 2 points, 0 and infinity. And this isometry fixes infinity. There is in fact a general statement that in discrete groups, you cannot have two infinite order elements fixing a common point on the boundary. So if you have two hyperbolic translations, or if you have a hyperbolic and parabolic translations in an isometry group, in a discrete isometry group, then they cannot have a common infinite point. And the proof, so the claim that this gamma generated by those two guys is not discrete, and now we're going to prove it. In fact, this general statement that if you have two infinite order elements with a common fixed point on the boundary, right, then this group is not discrete. This fact can be proved similarly to this, with the only thing that it's a little bit more complicated to do it in general than in this certain example, right, in this example. So let us do it. Consider the following element Hn, which is the conjugation of G2 by G1 to the power of n. Obviously, this is an element of the discrete group gamma, right? It's just that some composition of G1, G2, is like some word of G1 and G2. Both G1 and G2 and their powers belong to gamma. Okay, then Hn, this element, we just try to find how it acts on the point Z in the upper half plane. So first we apply it from right to left, right? So G to the 1 to the power of n is just, it maps Z to 2 to the power of n Z. Then we apply the translation plus 1, and then we divide by 2 to the power of n, since I took here G1 inverse to the power of n. Okay, but then this is equal to Z plus 1 over 2 to the power of n. Great. Then for every Z, we have the following sequence of points, Zn, which are the images Hn of Z. Obviously, since Hn is an element of gamma, Zn belongs to the gamma orbit of Z, right? Okay, great. But then you notice that Zn, which is written right here, it converges to Z as n tends to infinity. And thus, you have a non-discrete orbit, right? This orbit is not discrete since you have some accumulation point. So obviously at some point the elements Zn are very close to each other. Okay. Then, so yeah, this, but important fact, like an important general fact, is that so the issue is that these two isometries have a common fixed point on the boundary. That's an issue. Okay, now I want to define a very important notion of the theory of discrete groups, and this is the notion of a fundamental domain. Okay, so a closed domain D, domain here basically means that it's the closure of some connected open subset of X. Then it is said to be a fundamental domain for a discrete group of isometries gamma if the first condition, X is covered by the union of copies of D under the gamma action, right? One can just simply write that the right side is just capital gamma times G, right? This is basically how it can be simply written. Okay, the second condition, so the first condition implies that actually every orbit of gamma intersects with D, right? The second condition, let me formulate it carefully. The second condition gives the following. The interiors of two copies of D can intersect only when these copies are identical. So different isometries can give you different interiors. The only possibility is that you can have two adjacent domains that are touching each other on the boundary, on their boundaries, right? Well, with respect to, I would say that they can have some common boundary points, but the interiors should not overlap, okay? And so in fact, this means that the interiors are represented, so the interiors consist of the unique representatives of each orbit, right? So you cannot have 2 points from one orbit inside your fundamental domain D. You can have 2 points from one orbit only on the boundary of D, not in the interior. Great. And the third condition is the condition of locally finiteness. It means that so it's stated as follows. For every point P, there exists some neighborhood small enough such that the number of elements gamma such that gamma D intersects non-trivially with this open neighborhood. So you can only have a finite number of such elements gamma, right? So the number of elements gamma such that gamma D intersects non-trivially is finite. And again, if your point P is the interior point of D, right? Then you will get you will basically get only one copy intersecting this open bulb, right? If you choose the bulb really very small. But on the boundary, it's allowed to have like finitely many, and generally it can be a pretty large number, especially if there is a point such that it's, say it's a vertex of really a lot of triangles, I don't know, something like that. Okay, then generally fundamental, so let's consider some examples. Generally, fundamental domains are not uniquely determined for discrete groups. So an example with this translation group acting on the plane, I can give you two and actually really many different fundamental domains. what is interesting that they all have the same volume, right? They all have the same measure, but these are not even, so here these are not even convex, right? I just chose, sorry, I just chose some tiling, but you can do more, really. Okay. Another example is we already considered this action by Z, which is generated by hyperbolic translations in the upper half plane. Then in this case, again, so this is my orbit, and the fundamental domain for this action is just the strip between two geodesics orthogonal to the axis of my translation. You can notice that if I take, say, this strip, this is my strip, right? Then my translation with respect to the vertical geodesic, it sends this strip to the next one, and then to the next one, and so on. It gives me the tessellation by the copies of this strip, right, of my, so this tessellation of my hyperbolic plane by the copies of this strip between the two geodesic lines. Obviously, they do not overlap, and obviously it's a locally finite tessellation. So for any point we have a, for every point we have a neighborhood that intersects only finitely many fundamental domains. The second example is, again, this tiling, but okay, wherever you have already some tiling, it already gives you like a picture of the fundamental domain. So here, in this case, we already tiled the H2 by copies of this ideal for a gun with 4 ideal vertices, right? So we have this guy. We tiled the plane by translations, and this is obviously the fundamental domain. So the green circles is just they show the orbit of some point. I can take this the center of my ideal for gun, and then it gives me this green orbit. So this is a discrete orbit, and you see the orbit in this case is kind of the dual. It's kind of like a dual. It's dual to the tiling of the hyperbolic plane, right? So every orbit has a unique representative inside of this ideal, inside of those ideal foregons, right? So you will not have any other green points for this orbit inside of this same ideal foregon. Yeah. So this is precisely the definition of the fundamental domain. I'm already close to switch to the blackboard. So the last definition I was going to write down is the definition of the cofinite and cocompact isometry groups. And a discrete group is said to be cofinite if the quotient x mod gamma, or which is the same as talking about D, has finite volume. So if it turns out that the fundamental domain is a finite volume, then my group gamma is said to be cofinite. And it is said to be cocompact if the quotient or the fundamental domain D is compact. Okay, now I want to switch. So I will turn off this, and I will write down this on the board. So let me stop sharing. Okay. Great. So let me now start with examples again. So cofinite. Okay, so first of all, the remark, right? That compact implies finite, right? Compact groups are obviously finite, right? Definitely compact sets have finite volume. So now my examples, co-compact and thus cofinite. And here cofinite but not co-compact. And my examples definitely with z squared acting on the Euclidean plane are obviously co-compact, right? This is a compact fundamental domain. However, my example with ideal foregone so this is the free product of copies of z. This is a cofinite. This ideal foregone has finite measure. And actually the area, right, the area of the ideal triangle, right? Remember that the area of ideal triangle it is equal to pi minus the sum of angles, right? So this is equal to pi, correct? But this implies that the area of P is equal to 2 pi. But P itself is not compact, right? It has 4 vertices on the ideal boundary, so it is not bounded in the hyperbolic plane. But P is not bounded. I can also find some nice tessellations of the hyperbolic plane. So take the Paul model. Let's write it B2, right? And then I'm taking the following tessellations. So this is my first lines. Now I want to take I will take something like that. These angles will be equal to pi over 3. So all these angles are equal. And here I have angles pi over 2 all the way around this foregone. And I'm taking now the reflection group generated by. So one can note that tiling probably will look like that. Okay, so let me write it pi over 3 here. So this is pi over 3, pi over 3. And then I am getting here, again, right angles. See? So we have vertices of, so in this tiling, we have vertices of valence 4, and this corresponds to all angles being equal to pi over 2. And we will also have vertices of valence 6, and this corresponds to angles pi over 3, since you will have 6 angles, right, meeting at the same vertex. So this is a nice tessellation. It gives you already a co-compact group of isometries in the hyperbolic plane. Okay, we will consider discrete group of isometries and reflection groups a bit later with more details, but this is the idea. Okay, then another important notion, and I think, yeah, so the second important notion is the commensurability. So let me write the definition. Okay, two groups. Gamma 1 and gamma 2 are commensurable. Okay, yeah, I will say that are commensurable. I actually want them to sit in the common group, right? Are commensurable if their intersection is of finite index in both of them. For both j equals 1 and 2. Okay. And another, okay, I will let this, I will denote this as gamma 1. So the notation is this, gamma 1 tilde gamma 2. And commensurable in the wide sense, if there exists some G in the full isometry group such that gamma 1 is commensurable in the standard sense with G gamma 2 G inverse. So why this all this is interesting? I'm going to write down the following. Okay, I will say that it's a theorem. Okay, so the theorem is that if, first of all, if you have a discrete group gamma and it is cofinite, then the volumes of all choices of the fundamental domains are the same, right? So let gamma be a discrete group. And cofinite. And D1 and D2 be different choices of fundamental for fundamental domains, right? So for fundamental domains. Then the volume of D1 is equal to the volume of D2. This is the part 1. Part 2 is if gamma 1 and gamma 2 are just subgroups in isome X, and they are commensurable. So if gamma 1 are commensurable subgroups of isome X, then gamma 2 is respectively discrete, cofinite, or cocompact whenever gamma 1 is respectively discrete, cofinite, or cocompact. And so now let us consider some examples, I guess. So in the rate, it was already mentioned that for different choices of translation groups in the plane, we have this fundamental domain D1, and for the same precisely lattice Z squared acting on the plane, we can find another choice, right? So these domains are all of the same volume. Okay, let's consider another example. So let gamma be a finite index subgroup. So suppose that gamma, I don't know, let me find some nice example. Okay, actually, let gamma be a reflection group, right? Be the reflection group in the sides of the Euclidean square. So this is my remember that the orbit was, so let me draw the orbit. So I'm taking the point here and I reflect it there. Then I need to reflect it to the top and then I obtain this, right? And then I'm taking, so I will just write, we will just see how the squared is sitting here. Oh, no, it's a mistake. So here, no, wait a second. Yeah, here they should be close. But then, and it's only like that, right? So I claim that gamma. In fact, this gamma can be written more precisely, but the claim is that gamma is commensurable with the group Z squared. Right? This is my claim. And so I'm telling you that you need to take the vectors u and v, where u is 2 u2, v is 2 u1, right? And then my z squared is just generated by, well, it is the translations tau a, where a is the vector m u plus n v, where both m and n are integers, right? Okay, so how it goes. Let me now take the, and so let's choose this point, right? We can notice that the translation tau u, right? Okay, I first want to write it down. So I want to write gamma as the following group. It is generated by 4 isometries, 4 reflections of order 2. And it can be written as follows. It can be written as Z2. So this is the cyclic group of order 2, right? So this is the free product of Z2 and Z2. Okay. Direct product Z2, free product Z2. Okay, is it correct? Let us think about that. So the free product of 2 Z2s gives me the translation, right? Yeah, I think it should be good. So I have no relation between these 2 generators and these 2 generators, but the generators from these 2 sides pairwise commute, right? So the reflection here and the reflection orthogonal to it, both 2 reflections, they commute with those since the angle is pi over 2, right? The composition of these 2 reflections is just the central symmetry, and it doesn't depend on the order. So this gives us this decomposition. I think it's correct. And in fact, I'm taking one element from here, translation, and the translation from here, and it gives me the subgroup Z squared sitting in, so Z squared is just the subgroup of gamma. And what is the index of index 4? And indeed, let us find the orbit of Z squared. So Z squared is generated by such translations. So I'm taking one reflection and another. So this is my orbit with respect to Z squared. Then this is my element from the orbit. This is the elements from the orbit. So it seems to me that the fundamental domain for Z squared is this large square. So it's fundamental domain for Z squared. okay, this big square. And you see it has 4 copies of my fundamental domain for gamma. So this allows to compute us the index. So generally, if you pass to a finite index subgroup, you will just obtain the fundamental domain. So if the index, say, is equal to, I don't know, k, then your fundamental domain of the subgroup will be k times bigger. And this volume basically will be just k times bigger, right? So the cofiniteness and co-compactness and discreteness are preserved by this. Okay, so this is for reflection. This is this example with reflection groups. Okay, so as I said, the fundamental domains of discrete groups are not uniquely determined, but in some cases they are. And let me switch to the right board. Okay, so let me say, however, sometimes fundamental domains are quite rigid. Now let me define that a reflection group. So by definition, a reflection group is a discrete group generated by reflections in hyperplanes. So by this short term, we will always mean discrete groups generated by reflections. Generated by reflections in hyperplanes. Of X. Okay, and for reflection groups, the fundamental domains are already very nice. So let me first consider the following picture. So assume that I have 2 reflections, right? H1 and H2. Then the composition RH1 and RH2 is the rotation okay, let's suppose X is now the Euclidean plane. So let it be the plane. So I have 2 lines. Then the reflection is just the rotation. So if H2 goes first, okay, let me change this here to H1 and here to H2, right? I first apply H2 and then H1. So it goes like that, right? So this is the rotation. It is the rotation at angle 2 alpha around the point O, which is the intersection of these 2 lines, right? And discreteness implies that this should be actually a finite order element, right? So continuing this, I do not want I basically have like cones, and I do not want the cones to overlap. And also I do not want to have any accumulation points, right? So discreteness of gamma generated by these two reflections implies that it implies that actually 2 alpha, what does it mean? It means that 2 alpha multiplied by some number m should give me 2 pi, or so here is some tricky part. I can take something like with angle 2 pi over 3. It's still not a big deal, right? The images will overlap, but the group will be discrete. But I assume that alpha is, so I assume that alpha is less than pi over 2, okay? So alpha is less than or equal to pi over 2. Then 2 alpha multiplied by m is just equal to pi, right? Basically, this is implied by discreteness and by the fact that the cones do not overlap, right? Thus, alpha is equal to pi over some number m, where m is a natural number. Okay, great. So generally, in higher dimensions, we will have rotations around some codimension 2 plane, which is the intersection of H1 and H2. And the group generated by R1 and R2 will give us some dihedral, it is the so-called dihedral group. It's a finite group which will preserve the codimension 2 plane. And it will still give me the fact that the angle alpha, just repeated several times, should give me the full, like it will be the full path around the, now around the plane. And similarly, the angle will be equal to pi over some natural number n. Okay, how to do it, how to construct the fundamental domain for reflection groups in general. In general, the fundamental domains are constructed as follows. So in general, if gamma is a reflection group, then take all hyperplanes H alpha fixed by reflections are alpha and gamma. And so on. So I'm just drawing something. It actually, it doesn't matter what exactly is drawn, but something is drawn. So I just then consider X minus the union by all alpha of H alpha, right? The hyperplanes are fixed, so we know that they belong to the boundary of my fundamental domain, right? The fixed points of some non-trivial stabilizers can only be the boundary points of my fundamental domains. It gives me some union of connected like basically gives me the union of connected components, and choosing one connected component of this gives me, so let me define this, I don't know, as okay, consider X minus the union of H alpha, and pick a connected component and pick its connected component. E. This is the fundamental domain for gamma. So let's get back to this example. So remember, we had a group generated by reflections in the sides of the squares in the tiling. So basically what we did right there is just take all horizontal and vertical lines, cut them out, right? Then you will get the tiling by open squares. Choose any of them and you'll get the fundamental domain, right? And okay, so generally we want actually to understand when the groups are cofinite, co-compact, finitely generated, and so on. So in this particular case, I took the group gamma generated by all reflections, but in fact I obtained the group generated by just 4 reflections in the sides of my triangle. There is a general method that allows to, so there are basically, next time we will study the following general methods. The first method allows to construct a fundamental domain as a generalized convex polyhedron for any discrete isometry group. The second method allows you to describe a group in terms of some generators and defining relations for them, given some fundamental domain. So once you have a fundamental domain, it allows, there is the Poincaré method that allows you to obtain the presentation. If your fundamental domain was finite volume, if it was a finite volume convex polyhedron, then the Poincaré method gives us actually that the group is finitely generated, and one can really write down the generators and defining relations. And I think that we will consider some examples, including the modular group PSL to Z. I did not mention this example today because it's really more interesting to consider it together with the fundamental domain and together with the reflection group commensurable with it. So this will be, so the next part of the next lecture will be devoted to this very classical and famous example of discrete group. And I think that, yeah, so probably next time we will discuss those methods. Perhaps if time permits, we will consider lattices and Lie groups, but I'm not sure if I will have enough time for that. Okay, thanks very much for your attention. And well, should you have any questions, please let me know. Yeah?
elliptic connector K is elliptic or trivial, something.
Mhm.
Is trivial mean like identity?
Yes, yes, it's just the identity. Yeah, so you cannot get the identity as the identical isometry that fixes everything, right? If you take hyperbolic or a parabolic one. So if you take a parabolic isometry or a hyperbolic isometry and then you consider some powers, you will never get the trivial isometry that fixes everything. But for some of the elliptic elements may give you this isometry. So if your elliptic isometry is of finite order, this means that some power is precisely the identity. Yes, I actually didn't. That's a good question. I actually didn't write down anywhere. Let me to record. I want to write it down somewhere. Just let me use this part of the board. If remark, if gamma is discrete, right? Then all elliptic elements of gamma are finite order. Are finite order. So generally, right, as I told you, the elliptic elements can be of infinite order, but if this is an element of a discrete group, it should be a finite order. Why? Since if the element is a finite order, this theorem you just asked about, it tells you that finite order element is, so what's the problem? Well, I even don't need this theorem. This finite order elliptic element, so if an isometry is elliptic, it fixes just some point in the space. So it belongs to the stabilizer. The stabilizers are finite. Since this is elliptic elements of gamma are subgroups of the stabilizers, right? An elliptic isometry, it fixes some point x, which means that it belongs to gamma sub x. But gamma sub x is finite. So my isometry f belongs to some finite subgroup, and this implies that the order of any element is finite, right? Of any elliptic element is finite. And moreover, the stabilizers consist precisely of elliptic elements, right? Since they fix some stabilizers of points in the hyperbolic space or in some other space, they fix some points, so they definitely are elements of stabilizers, and thus they're elliptic. So it's so in the case of discrete groups, this behavior is a little bit more simple in some sense. Yeah. So this is the discreteness of gamma is quite a restrictive notion. Okay. Any other questions? No. Okay. So then see you next time on Thursday.